Yeah, so hi everyone, as Fabian said, my name is Rowland, I'm the lead developer at Tracktion, and today I'm talking about using JUCE ValueTrees and modern C++ techniques to build large-scale applications. If I can get my slides. Okay, so a couple of quick notes before we get started. All the slides are numbered, and there are quite a lot of examples, so if you want to ask a question about a specific example, remember the slide number so I can get back to it really quickly. Also, all the slides and examples will be on GitHub. Maybe not today, it depends how busy the conference is, but probably this week. And also, some of the coding style is squashed onto a slide, so don't think that's how I would normally condone writing code. So why have I chosen to speak about value trees today? Well, essentially, value trees are a way of building applications really quickly. A few years ago, we restructured the Tracktion code base. We've since changed the name of Tracktion to Waveform. To use value trees, and we had to learn a lot of things in the process, but essentially we have a much better code base now, and I wanted to share some of the things that we learned along the way with you. So I've got a quick demo here of Waveform. This is our current iteration of our DAW, just to kind of show some of the things that are possible and how this stuff does scale to quite large applications. So here is a slightly out of kilter version of our DAW. So it's a classic DAW. If you're familiar with that, we have tracks down the left-hand side, and then clips in the middle, and then plugins on the right-hand side. And if I zoom into one of these MIDI clips here, you can see we've got hundreds and hundreds of MIDI notes. And if I zoom in a bit more, the editor will pop out. And then if I open the MIDI editor, if I can see it, and zoom in a bit more, and then I can, drag a bunch of MIDI notes. As I drag these around, you can see the other view is updating. We've got the pitch in the properties panel updating. I can also do things like drag the velocity up and down. You can see, all the properties update. All the interfaces stay in sync, which is quite cool. And then if I select one of these plugins and open our mixer view, you can see we've got several views of the same plugin, and as I drag the EQ graphs around, all the EQs update, and of course there's an audio representation of that in the playback graph as well. So that was just like a quick demo to show that this is what we're doing with value trees. So back to the slide. As I said, about 4 years ago, we did this restructure to use value trees. And in the process, we took about 500,000 lines of Tracktion code. There's also about 600,000 lines of JUCE code that it heavily relies on as well. And basically, we managed to get rid of half of that. So now the code base is about 250,000 lines of code. It's been growing steadily since then. But the biggest place we managed to get rid of a lot of things was in undoable actions. If you've ever had to write undoable actions, they're a real pain because you essentially have to do something one way, it back, and every time you do something, you need to write one of these. That happens all automatically with value trees. So let's look at this process in a graph format because we like graphs. If we look at the features that we added kind of over year, this is how many features we were able to add each year. You can see real slow progress to begin with, then there's this sudden uptick, and you can see, yep, that's when we did the value tree refactor. If we look at the number of bugs, we also fixed a load of bugs in the process, and now, next to no bugs. Of course, that's just a bit of a joke. There's probably still bugs in there, but not on my watch. But lines of code, that is a much more real metric. There are now a lot less lines of code, and that is important because it means there's a lot less we have to kind of think about when we're working with a code base, when we're adding features. It's now a lot simpler to use. And all of this leads to more fun, and really that's the only thing that matters. It was a real struggle to begin with, and then now we have so much more fun. And a part of that is being able to go from meetings and start typing and getting ideas from your head into something on the screen. And that's why we have more fun using the code base. So what I was going to do today was talk about an overview of value tree and all the related classes, including var, identifier, value. So I wrote out a bunch of examples, and then I talked through them, and it took me about an hour and a half, and I didn't even get onto any of the fun stuff. So what I've done is I've left the slides in, and the examples will be on GitHub, and there's basically an example for every kind of use case you might want to use. Just a real simple example, so check those out if you want to. But what I will be talking about 5 of the most important things when dealing with value trees, and that includes callbacks, lifetime, those things, and then how to kind of build abstractions around value trees to build up applications. So unfortunately, this is all the good stuff we have to skip out. But we do arrive at the top 5 things to know. So first of all, is everyone familiar with XML here? Hopefully. OK, so this is a standard bit of XML we have on the right-hand side. This is our edit format or our project format in Tracktion. And ValueTree is very similar to XML. If you're familiar with the structure of XML, then you'll be familiar with the structure of ValueTree. The only real difference here is that we don't have text elements in ValueTree. Everything is an attribute. So imagine if you could create like a JUCE XML element, but you could listen to it to be notified when things change. So that's when properties change, when children are added or removed, or even the order changed. And that's essentially what ValueTree is. And it sounds simple, but it's incredibly powerful. There's a few terminology differences if you are used to XML. First of all, an XML attribute becomes a ValueTree property, and an XML tag becomes a ValueTree type. So the types are in blue here, the properties are in green, and their values in red. So just kind of remember that terminology. So what does a ValueTree look like under the hood? Well, ValueTrees are essentially a lightweight object that manages a reference-counted shared object. Okay? So the shared object inside is kept alive by ValueTrees, and it contains a name-value set of properties. And a name-value set is essentially a key-value pair set of vars. And it's ValueTree that provides the interface into the shared object here. So you don't really need to know that this shared object exists, but it's useful when dealing with lifetime to know that it's a reference-counted thing. And because it's reference-counted, ValueTrees are really cheap to copy around. So they're essentially free. They're just an atomic reference count. Because of this, when you register a listener, the only difference that all the data is stored in the shared object, but when you register a listener, the listener is stored with the ValueTree, not the shared object. Okay? So this means that it's usually best to take a copy of the ValueTree and register as a listener to that. So this enables us to write our AI code like so. So if we had a widget that is interested in changes to this ValueTree, we just inherit from ValueTree listener and take a copy of the state, and then we can add ourselves as a listener. And you'll notice there's no destructor here. We don't need to remove listener or anything like that. When the ValueTree goes out of scope, so does the listener list. And the call graph when you change something to a ValueTree looks something like this. This is an example of set property. So we call set property on a ValueTree. Remember I said ValueTree has the interface into the shared object. And then we call, it internally calls set property on the shared object, which goes into the name value set. It iterates all the properties, looking for a matching identifier that you pass set property. It then assigns something to the var object associated with that, then goes back to the shared object. And the shared object does have a list of all the ValueTrees that have listeners. So then it starts iterating those listeners and calls the ValueTree property changeback for those. Once it's done with that list, it goes back to the shared object's ValueTrees with listeners and goes to the next one and so on. However, you can kind of ignore this shared object middle. You can just think of setting property calls listeners registered with ValueTrees. You might have noticed in that graph, there's no kind of asynchronous things or arrows flying out into nothing. So callbacks with ValueTrees are synchronous. So don't do anything time-consuming in your ValueTree callbacks. In the example I showed at the start when I was dragging some MIDI notes, you get a property change message for every note that's changed. So if you do something complicated like try and sort the notes in that callback, you're really going to slow down your UI. So what you can do is either use dirty flags or async updaters to combine actions from multiple property changes and then act on it later. The other thing to note here is that callbacks iterate upwards in the tree hierarchy. So you get callbacks for anything that you're listening to on a higher level if things change lower down. So in our project format that I showed in the XML, we have an edit and then tracks, and then the tracks contain clips, and then the clips might contain notes. What we do in Tracktion is we have an edit tree watcher whose sole responsibility is to rebuild the audio graph. So we listen to our edit, and then anything that changes in the value tree, it could be a MIDI note, it could be a clip start time property or something, we can listen to that and then use that to rebuild the audio graph. And that's really powerful because it means we can delegate all that functionality. There's now one place in our app where we rebuild the audio graph. Before, there would be calls kind of all over the place rebuilding the audio graph, and it's easy to miss one out. Now there's one place to go and look for that. This does mean that you kind of need to take some care when designing your tree structure, and remember to check the tree types and the properties in your callbacks so you accordingly. And this is an example of how you would do that. You just inherit from ValueTree listener, maybe async updater, and then when you get your ValueTree property change, you can examine the type and the property that changes, and then trigger an async update, and then you would sort your notes. It's easy to assign primitive data types and even things like strings to ValueTree. They're just quick and easy. However, we're often dealing with slightly more complicated data than that. And what we can do with more complicated data is your first port of call should be really to just serialize it to a string. So think about efficiency here. Most of the time you're just setting a property and then you're not really worried about it that often. Most things in your app don't change constantly. If they do, you may need to think about a slightly different paradigm that we'll talk about later on. So what you can do here in waveform, we have a set of time stretch options which determine how we apply time stretching algorithms to audio clips. And if we provide a constructor that takes a string, we just tokenize the string that we get and then assign our members based on those values. And if we provide a toString method, we can serialize a thing to a string doing the opposite. And then we would just use this like so. We'd have the time stretch options, we'd set our flags, and then we can just set property by converting that to string. And if we want to print it back out again, we just get the property out of the value tree and convert it to a string. And you can see the output would be that string property stored in the tree. So now that we've kind of dealt with some of the basics of ValueTree, how do we start building applications? As I said, this is the same XML before, but we're going to be using this in all the examples, so kind of try and make a mental picture of it, specifically the clip and the start time. And you can kind of see that here, these naturally fit the hierarchical nature of applications. If you were designing an app, you'll probably start with a pen and paper and go, okay, well, I'm designing a door in our example. I'm going to have a project, and then there's going to be tracks, and then the tracks are going to contain clips. And then from that, you can start to go, okay, well, what's my data model going to look like? And it's probably going to look like this hierarchical structure. So what you can do then is start thinking about how am I going to code this? And from this XML structure, you can say, okay, well, I'm probably going to need an edit class. I'm probably going to need a track class. I'm going to need a clip class. So you can already start fleshing out your headers. And then you can say, well, what are these classes going to contain? And they've already got properties here. My clip needs a start time and a length. And I'm going to need these to be member variables. So it's a good way to start thinking about your classes. Once you've kind of got what your classes are, you can start thinking about how they're going to interact with the rest of the world. And with ValueTree, because we have this callback mechanism, we can essentially use this as an MVC paradigm. Now, in ValueTree land, I like to think of, if you compare it to MVC, that ValueTree essentially takes care of the model. That's the name value set data bit under the hood. And then the controller is this listener interface. So it kind of takes care of the model and the controller aspect. So really all you need to think about is the structure of your data and how you're going to represent it. And you can write multiple views to represent this data. So we can have EQ graphs, or you could have a bunch of sliders. And as long as you let the callbacks tell you when something has changed, you're always going to be up to date. So that's kind of classic MVC style, just reflect the data model. And you can have multiple views if you want in any kind of format. So I've got a real quick demo here. You don't need to actually examine the code. The example will be on GitHub. But I wanted to show you how quickly you can write an application. So that's number one, yep. So what I've got here is a slightly adapted version of the ValueTree demo that's in the JUCE demo. It's essentially a real basic door. It doesn't do any playback. But I've got my tree structure here, my tracks that are collapsible, and each of the tracks contains some clips. So I have this properties panel that I can rename things. And I can set the colors. And then if I can drag and drop clips around, and I can change their start and length. And of course, I can undo all this. So really easily, I can just undo everything that I redid. The other thing we also get is serialization. So if I close that and run it again, it's on my other screen, you can see that all the changes I just made are still there. Real quick run through of the code. Essentially what I've got is some helper functions to retrieve some value trees from tree view items, some helper functions to move the tree and create the default project. Then what I've really got in terms of UI is this value tree item which inherits JUCE tree view item, and it's a value tree listener. We take the state that we're going to represent and an undo manager so we can transaction things. Then we just register as a listener to that state, and we take a copy of it so we don't need to write the destructor. Then we've just got a bunch of tree view item overrides. We need to paint the item, so we're just getting some properties out of the tree like the color and also the text in this get display text method. More tree view stuff just to kind of resize, lay it out. But really the only value tree interaction we're doing here are the callbacks. So when we get a property change callback, we simply repaint the item because that's going to be the color or the name or something. And then when a child is added or removed or reordered, we just do a brute force, clear all the sub-items, iterate all the child trees, and then create a new tree view item for that. And then we just have clips and tracks, which basically just have slightly different drag behavior and slightly different text. And that's basically it. There's also a selection panel, which is just a component with some labels and sliders. And then when the selection changes, I just find out what type of thing changed and then just get some properties as values and assign those to the JUCE sliders or text editors. And it's really as simple as that to kind of hook up properties to UI. So if we break that app down, we've got about 750 lines of code, and that 750 lines of code includes the tree view of the data, that's the UI thing, the selected properties panel. It includes the color picker, the drag and drop, and undo, redo, and serialization. And specifically those last three things are really, full-featured app functionality. They're quite time-consuming to do normally, but we get them with little to no effort here. If we break that down a little bit further, we get 250 lines of UI code, which is always a big bulk of your code. We have 250 lines of reusable helper methods, so that includes saving the value tree to and from a file, and also some component helper methods I've got. And then there's about 250 lines of value tree interaction. So really a very small app for quite some high-level functionality. So a quick note on undo redo, because people often miss this because it's so simple with value trees. When you set a property or mutate a value tree in some way, then all you need to do is supply a pointer to an undo manager, and that will become an undoable transaction. When you hit undo on your undo manager, it will simply revert back to whatever the state was before. So you can either set a property or add a child. In the following examples, I've passed null pointer here, just to kind of keep the code examples a bit smaller. So now we've kind of built an app just based around raw value trees, just looking at them. We now need to think about how does this scale to larger applications. So interacting with the value tree directly, as we've just done, is quick, but there are some pitfalls. First of all, we don't have any type checking. We don't know what type of data is stored in the properties of the value tree. And we don't have any verification or bounds checking. It's perfectly reasonable to set negative start times. There's nothing that's going to catch that. And it also requires hidden knowledge about the data properties in the tree structure. If we're setting the start time property, then we need to know that that is just start. It's not start time or start time seconds. And that can be a problem, especially if you've got people new to the code base. So in C++, we like abstractions. We like type safety, and we like efficiency. We like the compiler to tell us when we've done things wrong. So we can start to get all this stuff back by building wrappers around value trees to bring all this into existence. So what this might start to look like is if we were creating a wrap around our clip object, we would have a struct that is our clip. We take a value tree that's going to be our state, and we take a copy of it so it doesn't, we don't end up calling a dangling value tree if we had a reference or a pointer to one. We can then start introduce our type safety, so we can say, okay, return me the start here with our accessor and set the start with our mutator method. We can apply const here to say this isn't going to mutate the state. And we can internally deal with the property name. So we're using an identifier here called start, which means the rest of the world doesn't need to know what that property is called. And in our set start method, we can either throw an exception or assert that the time is positive. What this is saying that if you set the start time to be something less than 1, you've abused this class. Or we could just deal with it silently and use a JMax, depending on what is good for your application. And we can start to deal with more complex objects such as color, and we can automatically do string conversions internally so the rest of the world doesn't need to know how our color is stored in our value tree. And if we were going to use this, we would create our clip state, create a clip from that clip state. We'd call setColor. If we tried to set -1, we'd get an assertion or maybe throw an exception. When we call setColor, we can set the color as red. And then if we output that using an XML string, you can see that we've corrected our -1 error here, and we've got a nice hex code for our color. So we can start with that process, but we can then move one further and use CachedValues to reduce the accessor mutator boilerplate. So with CachedValues, they're kind of like working with properties that some other languages have. I don't know if you've used Objective-C properties, but they're kind of similar to that. So what we can do is just in our constructor, we just have our cache value that wrap a data type, and then we refer it to our state, give it a property referred to, and the third argument there is a null pointer, an undo manager that can be an undo manager if you want it to be undoable. So we can use CachedValues to remove a lot of that bloat and supply an undo manager. And now we've still got the type safety here. We can now only assign color objects to color. We can't assign it a string, for example. But we have lost something from the previous example. We've lost our range check-in. We can now set -1 to our start time, and there's nothing that's going to fix that for us. Quick note on using non-primitive type cache values. All you need to do is specialize this variant converter class for your custom data types and do the conversion to and from a var, which is kind of dead simple. And then this is going to be available for your whole app, so you know your conversions are going to be the same. Again, we just use that in the same way as before. We create our value tree state, we create a clip to wrap that, and then just assign some values to our properties, and we can see that we've got this -1 bug here. So how do we go about fixing that -1? So although CachedValues can contain data types, we can abuse this by creating a wrapper around that data type. So what we've got here is a constrainer wrapper. So our cache value is going to contain a constrainer wrapper that's going to wrap a data type. So if we take our start time, for example, our first template parameter would be double because we're wrapping a double. And our second template parameter is the constrainer that we're going to use. So we take a copy of the data type as our member, which is going to be our cached version of it. And then the real magic happens in this templated constructor. Because we're going to be creating these on the fly when assigning properties to CachedValues, by providing a templated constructor, we can create one of these from a double. And that means that we can get a double and call our constrainer constrain method to constrain the value that we're using as our cache version. We also need to look like a primitive data type or a data type that the cache value can deal with. So we need to have a few more methods. We need to provide a copy constructor because these things will be copied around. We also need to provide equality and non-equality operators. And we need to be freely convertible to vars and our underline type here. And we can also call our constrain there as well. So building a constrainer is dead simple. We just need to implement a constrain method for our start time constrainer. All we do is construct a range, say we want it between 0 and 42, then we can just clip the value and return that. So when we use our cache value, we just create a cache value with a constrainer wrapper, our double, which is the underlying data type, and our start time constrainer. And now you can see that if we use this in the same way as before, we set 0, we get our output of 0. If we try and set 10, we get 10. Now we're trying to set 43, which is outside of our range, and the constrain method does its job and constrains it to 42. And our -1 problem goes away. We've got 0. We can make this slightly more generic by using template arguments to specify the range. So now we could construct our constrainer wrapper using a range constrainer and then provide 0 and 42 as template arguments. We can go one step further than that, so we don't just have to constrain doubles, we can constrain other data types. So we could constrain a string using a number constrainer, which retains only the numbers, or we could retain only the letters. So here we're just essentially constructing a new string from the letters, and we would just use this. If you look at the cache value line, we can see we've got a constrainer wrapper around a string that takes our letter constrainer, and then if we try and assign it a string of hello world, where the L's are 1s and the O's are 0s, we get the output hey word, because everything that's a non-letter has been stripped out. So in summary, it's possible to use templates to specify constraints held on CachedValues. Alternatively, you could create a version of CachedValue that takes a std function that constrains the contents. But the reason I've done it like this will become clearer, and it also means you can do it with existing well-tested JUCE code. You don't have to keep a copy of the class for yourself. So we've got one nice clip object here, and one clip object does not make an app. What we're typically dealing with is big lists of things. So in our door example, we've got a huge list of tracks. The tracks have a huge list of clips, huge list of plugins, and clips have a huge list of MIDI events and things. So what we could do is we could have each of our classes inherit from ValueTree listener and listen for when children are added, removed, or the order's changed, and then construct these objects and delete them. But that's quite a lot of work. What we want is an abstraction to deal with that for us. So we've created ValueTreeObjectList, which essentially does that job. It's much easier to deal with one of these because it's easier to iterate. It's a lot more efficient. We get all that enforced verification and the type safety as well. The other thing we get with this is we avoid lists of mixed types. So if you have a track, you could have a bunch of clips in that track, but you could also have a bunch of plugins. Now, if you ask for the track's number of children, that will contain your clips and your plugins. So either construct your hierarchy where you only ever store in one type, or you can use a ValueTreeObjectList, which will only construct clip objects, and then you can just say, hey, how many clips have you got? And you've got the number of clips. So what we're trying to avoid here is code like this, where we've got a track, we add a couple of children, and then we ask it for the number of the children. But as I said, that's only going to be valid if all of the children are clips. If we add another one, again, we've got the same problem. And then if we want to try and iterate these tracks, we need to check the type every time we're doing this. And then we might construct a clip if we want our type-safe methods that we just built. But constructing a clip might be costly. There might be extra work involved that we don't know. So we don't really want to have to do this on the fly. With a ValueTreeObjectList, what we end up with is a much simpler use, where we construct our track in the same way, but then we create a clip list around a track. We can then just ask it for the size of its objects, which we know are all going to be clips. And then we add another one. It automatically creates another object that we can just iterate through using a range base for and call our methods on it. So what does a ValueTreeObjectList look like? Well, essentially, it inherits from ValueTree listener, and it needs a state that it's going to mirror. So in this example, we're going to take our tree as our parent state. Then we have two methods. The first one is rebuild objects, which is essentially going to iterate the tree's children and try and construct an object for one of each of those. And then in the destructor of our derived class, we need to free all those objects as well. So that's kind of construction and destruction methods. The real business end, these three methods, is suitable type, create new object, and delete object. So is suitable type, we just examine the tree and return true if we're saying, yes, we can create an object for this. And then if we do return true, we're going to get the create new object call, which is going to pass us the value tree that we're going to construct an object to represent. And we simply need to return a pointer to that. And then when the tree is removed or the free objects are called, then we need to be able to delete that object as well. There are three other methods, new object added, object removed, and order changed, which are called for each new object that's added or when the order is changed that's outside of the rebuild objects, free objects. So essentially when things are added to the tree once you've already built this list. That can be useful for sending change messages and things like that. And what we end up with is just this array of pointers to objects that we can then deal with as a standard container. So an implementation of this, if we were building clips, would look like this. We would inherit our ValueTreeObjectList and build clip objects. We need to take our parent state, which is going to be our track, and we pass that onto our ValueTreeObjectList. We rebuild the objects, and we free the objects in the destructor, as I said. And then for each of the children, this is going to, we need to return true if we can build an object. So here we're just saying, if the tree type is a clip, then we create an object. Everything else we're not interested in. When we create an object, we're simply creating a clip like we did previously, and we're wrapping that value tree state. And we need to delete it. We're just going to call delete on it. So as I shown before, this is how we use it. We create our clip list, and we can output. We get number of clips is 2. Then if we add another value tree, the value tree object list is going to construct a new object, and therefore our objects now has a size of 3. And then we can use a range-based for to iterate, call type-safe methods on it, and we get our XML, which is a track with 3 clips, correctly with their color property set. So I've got another quick demo application here. So this builds on the previous example, but I've now got an extra UI element that uses a ValueTreeObjectList. I've got these arranged clips now. They're ValueTree property change list, and that's just a short way of saying I only want to inherit the ValueTree property changed callback. And here I'm just examining the tree type to say if it's my state that's changed and the name or the color has changed, I just repaint myself. And then in my paint method, I'm simply just drawing a color and the name based on some tree properties. In my clip list, which is my ValueTree object list, I'm going to be building arranged clips. I need to take the state that I'm going to be mirroring. I need to rebuild objects and free objects. In my resize method, because my arranged clips are components, I can simply iterate the objects and then lay them out based on their start and end times. Here I return true if it's a clip, because I can only create arranged clips for clip tree types. When I create a new object, I'm creating an arranged clip, but I can do an add and make visible here because they're components. This is really great for building UIs as well. And then I simply need to delete it if the tree gets removed. I do use these new object added, object remove, object order change methods here to call resize. So if a tree gets added, I make sure I do a layout of the UI. If a property changes, I can check that it's a clip that's changed, and then if the start or the length changes, then I can again lay out those elements. And this is an example of where it's actually really useful to know when child trees have changed, because you're often interested in that. So if I do a quick run through of what this looks like. Again, dead simple UI. This uses the same project as before. You can see it's even the same file. It's picked up those changes I made earlier. And then if I do things like change the track color changes. I can move clips around. Let's do a different one. Can change the length and the start, and of course if I drag that, then it jumps around. So, and then I can undo it. So relatively high level featured interface there, and that's only 200 lines of code to build that second window, which is really small if you think about how much is going on there, including all the drag and drop, drawing and reacting to things changing. We haven't talked about thread safety yet though, and that's always a big monkey in the room. Elephant in the room. ValueTreeObjectList is not thread safe, okay? We don't inherently have thread safety there. And that's usually because these things are dealt with on the message thread. Because ValueTree isn't thread safe, you should only interact with the ValueTree on the message thread. There's no internal lock-in or synchronization. And that's good because it gives us the performance and we can manage the thread safety on top of that. But if you do need access to objects from other threads, you can use reference counting to do this. So a neat trick is if you inherit from reference counted object in your objects that are being managed, so our clip could inherit from reference counted object, then we can increment the reference count in our create new object and decrement it in delete object, and then anything else that has a reference to that clip is going to keep it alive as long as it's got a reference counted pointer to it. So that means the clip could be removed or the track deleted, and if something else is referencing it, then it's going to keep it alive. If you are doing this, however, make sure you haven't got any back pointers to things that may have been deleted. If you've got a clip that's perhaps referencing a track that was owning it, you either need to get my slides back. Yeah, you either need to keep it alive by strong reference counting, or you need to keep a weak pointer to it. But to be honest, if you can get away with not keeping back pointers, that's usually the best way to go. And with ValueTrees, that's often quite easy to do because you can just keep the state that you're interested in. An alternative to incrementing and decrementing the reference count is to keep a copy in a reference counted array, and that's going to automatically manage the reference count for you. You can also lock that with a critical section, which means you can then return copies of the reference counted array, and you can do that from background threads, and it's not going to matter because the array is going to be locked. So a note on your method calls, these still need to be thread safe. Just because we're applying thread safety to our ValueTree object list, it doesn't mean that calls into the objects are going to be thread safe. So if we look at our clip list now, we can see that we've got this reference counted array with a critical section. I don't know if you can see that at the bottom. And then when we create our new object, we're simply adding it to that array, which is going to bump the reference count. And then we can, in delete object, we can remove that, and that's going to decrement the reference count. One quick note on this, if you're using an array like this and you're interested in the order, you want the order to map the order of the value trees, you're going to need to resort it when a new object is added, removed, or the orders change. Sometimes you're not interested in the order though. And what we end up with here is we can simply return the reference counted array using this getClips method, and as I said, that's going to lock the critical section, increment all the reference counts, take a copy of it, and then release the lock so you can add things. This is useful for low priority threads, so if you're building proxies or maybe detecting beats or something like that, you know, things that it's okay to use locksing. You might want to avoid creating a copy of the array, however, and you might just be interested in iterating the objects. So with this, we can either just provide access to that array, or we can implement a visitor method. So if we were going to provide access to the array, we'd just provide a const reference to the array, and then we have access to this critical section, and callers can lock that critical section to make sure nothing's added or removed to the array whilst we're using it. However, a better method might be to implement a visitor pattern here, and then you just pass a callable object in, and the lock is taken automatically. So that avoids callers having to apply their synchronization. This is not real-time thread safe, though. Don't do this kind of thing on the audio thread, because you'll get all kinds of priority inversion problems. Remember, value trees are essentially message thread objects. If you add a tree and then that thread kind of goes to sleep whilst it's holding a lock because it's in the middle of creating an object, and then your audio thread comes along and says, oh, I want to do something with those clips, it's then sitting on a lock that's waiting on a thread that's asleep in the OS. So don't do that. What you really want to do if you're dealing with the audio thread is take a copy of the thing that it references when you construct your audio objects, or you could use like atomic shared pointers to swap them around when things change. Cache value isn't thread safe either. You might think, well, hang on a minute, wrapping a float or a double, that's thread safe. It's not. It's what's known as a benign data race, which is still bad. Thread sanitizer will still throw up all over you. There's a great Intel blog article on benign data races. Read that for why they're bad. But we can inject some thread safety into cache values, and we can use a similar trick to what I showed before with the ranging or the bounds constraining to create atomic wrappers around these things. However, remember, this is only going to be thread safe for reading from different threads. As soon as you try and write to a cache value, it's going to try and write to the value tree, which, because there's no internal synchronization in the value tree, is going to cause a data race. So if you combine this with the previous ValueTree object list techniques, this enables you to kind of have thread-safe reads from all of your objects from all different threads. So what does our atomic wrapper look like? Well, similar to before, we need to provide an interface that looks like a primitive data type or a data type that a cache value can use. But now we're just taking a single template parameter, which is going to be our type. And I don't know if everyone can see, but down the bottom, we've got a std atomic type value, and then we default construct that. So this means that when we're accessing type, that's now thread safe. So we still need to provide this templated constructor because we need to be able to be assigned from primitive data types. If we're storing a double, we can wrap it in our atomic, but we still need to be able to assign it from doubles. So we can do our atomic store here. And then we've got the other methods that are implemented similarly to before. We're either storing to the value, or we're loading, and when we compare, we can load out the two values, do a comparison that way. And again, we need to provide operators to be convertible to var and to our type. You could also, using this, create a relaxed atomic version if you're really interested in performance. So in summary, what have we looked at today? We've looked at how ValueTree is similar to XML, but it's got a listener interface. It automatically handles serialization and undo redo, and also drag and drop is quite easy to get in there because you essentially remove a value tree from one tree and add it to another one. Those are all kind of high-level app tasks. Complex data can be stored by serializing to and from a string, as I showed, or if you've got a really complex data that better fits a memory block, you can do that. So we have track images that are stored as JPEG versions in memory blocks. We can ensure type safety by creating wrappers around value trees. And we can avoid access and mutators by using CachedValues and just referring them to properties. And then once we've kind of got our basic application, we can start creating lists automatically managed by ValueTree state using ValueTreeObjectList. And of course, we can enforce all our thread safety and bounds checking using CachedValues by creating wrapper types around the primitives. There's a few thoughts that I kind of want to leave you with that I haven't really got time to talk about here. Because value trees have this transactional nature, everything is either setting a property, adding a child, removing a child. You can kind of keep two value trees in sync as long as you mirror the operations on them. And JUCE has this really cool value tree synchronizer class that will enable you to do that. So every time you change a value tree, it essentially goes, oh, that property's changed, now I'll send that and apply it to another value tree. So what this means is that it's now really easy to create different interfaces, perhaps on different devices. So you could have your desktop interface with your kind of keyboard and mouse heavy thing, and then you could have your tablet that runs a really nice touch interface. And as long as the value trees are using some mechanism to keep them in sync, changing one is going to affect the other, and perhaps your audio is running on your desktop. If you can do this over kind of a small local network, it's interesting to think about how you could apply this to much further afield. So we could talk about perhaps having a value tree living in the cloud and as packaging transactions to that. Or we could think about sessions remotely. So we're kind of mirroring value tree state over the internet to people across the world maybe. There are a few places we can improve value trees and the various classes related to it. The big one I can think about is copying memory blocks at the moment. Means that you copying vars that contain memory blocks means the memory block has to be copied, but we could get around that with like a reference counted copy on write type trick. So don't be put off if you come across certain problems with value trees, because there's often ways to work around them or improvements. If they're not there already, it's just because we haven't come across the problem yet. So thanks very much. As I said, all my presentations and notes will be available on GitHub, and hope you enjoyed. Thanks very much.
Any questions?
One over there. Yeah, I have a couple questions, but I can start with one and then other people. Especially about the 500,000 lines of code to half of it, that like a giant refactor. How many people were working on that at the same time, and how much hours, months, years did that take?
It was me and Jules working. I think we did the bulk in about 3 or 4 months, and then spent about 2 months on top of that, kind of fixing all the things that we'd broken. So I don't know, maybe 4 to 6 months in total. But it was a big application.
Yeah, and then my question is like, would you have like a lock on anything, changing anything else about the code base, but you're only doing that refactor and not edit?
Yeah, we were only doing that refactor because it's quite difficult to also add features at the same time, and also to test new features whilst you're testing everything else that will have broken is quite difficult as well. So we were like, the boss wasn't particularly happy that new things were getting added, but we were like, this will be worth it in the end. And it totally is. It's so much quicker to add features now that it's value trees. Even just creating UI, I said a lot of that was undoable actions that we got rid of. But now assigning things to UI is at least half the size it used to be.
Yeah.
So.
Right. Okay, my other questions are mainly about the XML. So for instance, one is how combining the time stretch options into one string.
Yep.
What would you say is the threshold when that will become like a bad decision?
Your profile will tell you.
All right, yeah.
It depends. I would say if it's a relatively small thing that you would explain to someone else in terms of a string, then it's probably okay. If it's something that triggers a one-off operation, like we only apply our time stretching when we render files, so it just kind of reads it out, creates one of these time stretch objects and time stretch options, and then does the time stretch. And it's not like we're continuously reading that like we would a volume level or something. So I think you kind of just need to use your judgment. But I would say start with a string representation, and if it makes more sense to do it in a different way, or you're forced to. An example we have in Waveform is plugins keep their own state, But at some point, we need to get that out as a blob of data. So what we do in that case is the plugins just have all their state, but when we hit save, we kind of go through all the plugins and say, flush your state to the value tree. And at that point, we get the binary data, convert it to a base 64 string, and store that in. So at that point, it's all binary data living in the plugin. You could use that method, but only when we need to save it do we store it to the tree.
Thank you.
I just wanted to ask about sharing, like having this sort of shared global state as a value tree.
Yeah.
So the way I've done that is with a shared resource pointer with the whole, basically the whole application state in one value tree that gets passed around. Is there another way that you'd recommend to do that?
It's difficult because it depends what your... I have dealt with apps that have tried that approach before, but I find it gets quite messy. Maybe it's because I come from a more desktop environment where you can have multiple projects at once. So having like a shared thing that is your project makes no sense in that instance. But I have dealt with projects that say, hey, this is my app state and it's always on. And when I want to change it, I'm just going to pull out everything from the value tree and then rebuild it. And that means my UI doesn't need to change. But again, I'm not a big fan of that. I kind of like to have this. This is the front of my application, and it might contain your settings and things like that. And then you load a project because it's a very definite starting something. And that means then you can load your project from some XML or some data, and then build your UI to reference that. And then maybe you've got some audio things as well. So that tends to be how I do it. I don't really see what benefit having your kind of app state as a value, as like a shared value tree gives you. Unless you're storing things like settings. I think settings in like a shared value tree state are okay. So yeah, I don't know. It depends on your use case really and what your designs are.
Any other questions?
Yeah. Was this the examples that you showed, the code examples, are they going to be on GitHub?
I will put those on GitHub as well, yeah. They're really small. They're just like between 10 and 20 lines of code that first of all deal with vars and things like that and using variant converters and stuff like that. And then also they have all the ValueTreeObjectList and stuff like that if you want to use them.
Okay.
So.
Yep.
Thanks. Just a quick question, and to echo something you had said, you showed briefly how some of the UI objects like sliders and things have values inside of them.
Mm-hmm.
So you can do this nice refer to and then hand them a node in the value tree, and it takes care of all of the updates.
Yep.
And the really nice thing about that, since it's reference counted to, you can have 6 or 7 sliders all pointed to the same thing.
Yep.
We've done that, and it has made all the UI just heaps simpler, as you said. What I'm curious about, because I haven't looked so much at the audio processor parameters yet, you could probably do the same thing with like audio processor parameters, put a value object in there, have them pointing. And the only thing that we'd really have to worry about is the thread safety issues you were talking about, right?
Yeah, I think so.
Okay.
If you can make it thread safe, then it should be. You might run into performance issues. When I've written plugins based around value trees, I kind of have this set of parameters that will be atomic or something, and then the value tree kind of updates those, and then the audio thread picks up the atomic versions. So if you're dealing with plugins, you need to have like some kind of atomic layer in there. But you could probably just write a wrapper class around that kind of handles that automatically for you.
Okay, then please join me in thanking the speaker again.
Thanks for coming.